Okay, our group will be covering the applications of Le Chatelier's principle with the introductory activity as well as activity B.
So the purpose of this activity is to investigate 6 equilibrium systems to gain a deeper understanding of equilibrium and Le Chatelier's principle. So the hypothesis, according to our procedure in Le Chatelier's principle, the addition and removal of reactants and products should affect the equilibrium to shift in the direction to counter the change in concentration and restore equilibrium. Additionally, change in temperature should affect exothermic and endothermic reactions in opposite directions, and creation or removal of reactants or products should be able to tell us which type of reaction it is. So the materials for the introductory activity part A, which is the effective concentration on equilibrium, you will need 0.2 molar iron 3 nitrate solution, potassium thiocyanate 0.5 grams, potassium thiocyanate solution 0.002 molar and 20 milliliters of that, monobasic sodium phosphate 0.5 grams water, beakers, 2 beakers 250 milliliters and a graduated cylinder of 50 milliliters, hot water, ice, pen, petri dish, graduated pipette, 2 spatulas, 2 test tubes, and a test tube rack. This activity serves to create a base of knowledge in how stresses can affect the equilibrium of a reaction. So the procedure for part A of the introductory activity is step 1. Prepare 2 beakers of 125 milliliters of water, 1 hot and 1 cold for use in part B. Step 2. Measure 20 milliliters of potassium thiocyanate solution and pour the solution into a petri dish. Record the initial color and all changes that occur in part A and B. Step 3. Add 3 drops of iron 3 nitrate solution to different spots in the petri dish. Swirl until color is uniform. Step 4. Add half pea-size amount of potassium thiocyanate in one spot and wait about 60 seconds to observe changes. Step 5. Swirl the solution to dissolve them and record the color. Step 6. Add half pea-size amount of potassium nitrate in one spot, wait 30 seconds and record any changes. Swirl to dissolve until the color becomes uniform. Step 7. Add a fourth of a pea-size amount of sodium phosphate in one spot, wait 60 seconds and observe any changes. Swirl to dissolve crystals and record color. Step 8. Add 1 drop of iron 3 nitrate solution in one spot off to the side. Record any color change. Step 9. Add a pea-size amount of potassium thiocyanate in a different spot. Wait 30 seconds and record any changes. Keep this solution for use in part B.
Okay, so our introductory activity part A, step 1, we started out with 20 milliliters of potassium thiocyanate solution, and it's clear. After adding 3 drops of iron nitrate solution to the 20 milliliters of potassium thiocyanate solution, we stirred the mixture and it turned orange. Next, we added half a pea-size of potassium thiocyanate crystals in one spot. We waited 30 seconds and then stirred the solution to dissolve the crystals, and it turned a reddish-brown color. After adding potassium nitrate crystals to the solution, there was no color change. Next, we added 1/4 pea-size amount of sodium phosphate monobasic crystals. After waiting 60 seconds, no change occurs. And then we swirled the solution, which made it clear. Next, we added 1 drop of iron nitrate solution to the existing solution in one area. The area where the iron nitrate solution became a dark red splotchy color. And then we added a pea-size amount of potassium thiocyanate crystals in one spot. The solution around the crystals became more clear. The spot still stayed. Moving on to part B of the introductory activity, we labeled 2 test tubes as A and B. So test tube A is the control, and then we divided the complex ion solution into 10 milliliters each for each tube. Next step, we placed test tube B in an ice bath for 5 minutes. And afterwards, the appearance of the particles became more prominent and started to settle at the bottom of the tube. Last, we placed the solution in a hot water bath for 3 minutes. the particles in the solution started to rise, and that's it.
So basically, from the introductory activity, we learned that the addition of more chemicals will cause a shift in favor of whichever side's concentration is being lowered, and that the addition or removal of heat will cause a shift that is determined by the type of energy change of the reaction, whether it be exothermic or endothermic. And we could use this in our next activity, which is activity B. Okay, so for activity B, you're going to need ammonium hydroxide solution, 14.8 molar, 0.2 molar copper sulfate solution, 1 molar hydrochloric acid, 10 milliliter graduated cylinder, barrel type pipettes, stirring rod, test tube rack, and a wash bottle. Before you start the experiment, you're going to need to set up the compound with the initial conditions of approximately 5 milliliters, 0.2 molar copper sulfate, and in a fume hood adding the 14.8 molar concentrated ammonium hydroxide solution dropwise until you see a significant color change. Alright, so here's the system. It's copper sulfate reacting with ammonium hydroxide to form the copper compound. And the copper sulfate is blue, with the ammonium hydroxide being clear and the compound being sort of a cloudy light blue. Okay, so the activity B procedure can be split into two main parts. That's adding the HCl and then the two separate temperature tests. So we'll begin with the addition of the HCl. So we're going to be adding 3 drops of 0.2 molar HCl to the copper compound and waiting 60 seconds to observe the changes, swirling to dissolve and record the color. So the changes we actually observed from this experiment was a color change back to a less opaque blue, which means adding HCl favors the reverse reaction. This makes sense because adding the hydrochloric acid would decrease the concentration of the strong base ammonium hydroxide, causing a shift left. Basically, you could think of the ammonium hydroxide as the OH minus concentration and the HCl as the H plus concentration. For changes in heat, we both removed and added heat. So for removing heat, we placed the compound in an ice bath and waited 60 seconds, observing that the solution stayed cloudy. And for adding heat, we placed the solution in hot water and the compound seemed to dissociate, meaning that it favored the reverse reaction. So if it favors the reverse reaction, this means that heat will be on the product side, or basically that the solution is exothermic.
The system of copper 2 ions and ammonia reacted to form a copper-ammonia complex ion in the reaction shown below. When experimenting, the addition of clear ammonia to blue copper ions made the solution blue with some cloudy precipitate, which was likely the complex ion that was proposed by the experiment. The addition of hydrochloric acid in the second part of the experiment seemed to dissolve the cloudy precipitate, suggesting it was reacting with one of the reactants to cause the system to shift left. We thought that hydrochloric acid reacted with the ammonia since it is a weak but viable base. The heating and cooling of the system helped us to determine whether the reaction absorbed or released energy. When cooled, the reaction didn't show very much change, but when heated, the system seemed to dissolve the cloudy precipitate, or the complex ion product, which suggests that the reaction was exothermic since the heat caused the system to shift to left. Our experiment showed that the addition of both reactants to a system would shift the system to the left, favoring the products, as well as the opposite for products and a right shift. We also saw that other reactions could affect the reactant and product concentrations and cause similar shifts. In addition, changes in temperature can affect the system at equilibrium differently for exothermic and endothermic reactions. The type of reaction can be determined by the shift in the system that the change causes.